12th Science Chemistry Transition and Inner Transition Elements.
Hello students, in previous lecture we have studied detail about the electronic configuration and oxidation state of actinoids. Actinoids are nothing but these are the inner transition elements which is present in second inner transition series that are called as actinoids. And actinoids in which actinum, that is 89, having atomic number 89, to Laurentium having atomic number 103. These 15 elements are there which is present in second inner transition series, that is in which 5f orbitals are progressively filled. Then we will study detail about the properties of the actinoids and the differences between lanthanoids and actinoids and similarities in the lanthanoids actinoids. Then in this lecture we are going to study detail about the actinoids. Then first of all we will study about the general or specific properties of the actinoids. That is, see here first, that is properties of actinoids and the specific properties which is applicable to the actinoids. These are similar like to lanthanoids. These are also inner transition series elements. That means they are similar like lanthanoids. That means here in lanthanoid 4f orbitals are gradually filled up or progressively filled up. Similarly in actinoids 5f orbitals are gradually or progressively filled up. Then similar like to lanthanoids, these elements, the elements which is present in actinoid series, they are also shows silvery white colored elements are there. Few of the lanthanoids they are also silvery white color, and similarly few of the actinoids series elements are shows silvery white color. See here the next property, that is in actinoid series from actinium to Laurentium, thorium and uranium are naturally found radioactive elements, and in this series generally all elements are radioactive in nature. That means the elements in this series they are radioactive in nature. That means radioactivity, this property, that means here these elements emits alpha, beta, gamma rays from their nucleus and they are highly unstable, and therefore these are known as radioactive elements. Out of that uranium and thorium are natural, but remaining all are synthetic elements. Synthetic or man-made, these are also known as man-made elements. That means the except uranium and thorium, other elements they are prepared in the laboratory. That means they are artificially prepared in the laboratory. Then see here, as they are radioactive elements, that means it half-life period of thorium is 1.4 into 10 raised to 10 years, and that is of uranium 4.5 into 10 raised to 9 years. That means here, see here, half-life of those elements are very long. Uranium and thorium which having half-life period, their half-life periods are very long, therefore these are found in the rocks on earth. And other elements, that is protactinium, plutonium, neptunium, half-life of those elements are also greater or more, therefore they are long-lived elements. Then most of them have high densities. Most of them have high densities and it is nearly about 10 to 15 gram per CO2. That means they have high densities and they have also high melting point. It is nearly about 1000 degrees Celsius. That means it is greater than 1000 degrees Celsius and they have high boiling point, more than 3000 degrees Celsius. That means they possesses high melting point and high boiling point. The actinoids, these are the less reactive than lanthanoids, because of most of them are radioactive elements which are highly unstable. Reactivity of actinoids which is compared with the lanthanoid, that is, for example, lanthanoids. Any lanthanoid when reacts with water, it reacts with normal water or cold water and it gives lanthanoid hydroxides having formula LnOH with liberation of hydrogen gas. But actinoids, they reacts with hot water. That means generally they does not react with cold water, they react with hot water and forms their hydroxide in +3 oxidation state with liberation of hydrogen gas. That means here reactivity of lanthanoids is compared with actinoid, that is reactivity of lanthanoid is more than the actinoids. Then they also shows the higher oxidation state, that is +2, +3, +4, +5, +6 and sometimes they shows +7 and +8 oxidation state also by actinoids, but lanthanoid shows only +2, +3 and +4 oxidation state. Then see here why the actinoid shows higher oxidation state like +5, +6 and sometimes they shows +7 and +8 oxidation state. It is because of their 7s orbital, 6d orbital and 5f orbital which having nearly the same energy. Energies of those orbitals are nearly the same. Therefore, electron, that is differentiating electron, that is last electron which occupies the 6d orbital or 5f orbital. It may be occupies 6d or 5f orbital. In thorium, proctinium and neptunium, the electron, last electron, differentiating electron enters into 6d or it is enters into 5f orbital because of the energies of these three orbitals nearly the same. But from plutonium and onward, the elements plutonium and onward elements in which 5f orbital is regularly filled up or it is regularly filled up or it is gradually progressively filled up. Then see here there are one more important property of actinoid I am going to discuss it with you, that is actinoid contraction. Like lanthanoid contraction, actinoid contraction is shown by those actinoid elements. The name itself indicates actinoids, that means from element actinium to laurentium, which having actinium having atomic number 89 to laurentium having atomic number 103. Though the atomic number increases, the atomic radii or ionic radii decreases from actinium to laurentium. That means there is a contraction of atomic size or atomic radii as well as ionic radii from actinium to lawrencium. It is because of poor shielding effect that is exhibited by f orbital. As f orbital has diffused and complex shape, therefore it shows poor shielding effect, and therefore effective nuclear charge increases from actinium to lawrencium. Therefore effective nuclear charge increases as one extra electron added into the next element, and therefore effective nuclear charge is increases by 1 unit for the next each elements from actinium to lawrencium. Therefore atomic radii or ionic radii decreases from actinium to lawrencium, and that effect is called as actinoid contraction. And see here, that is lanthanoid contraction and actinoid contraction. Here actinoid contraction is more than the lanthanoid contraction. Then I am going to discussing with one more concept, that is here the property of actinoids are compared with the properties of lanthanoids. That means we observe the few properties that is similar in those both lanthanoids as well as actinoids, and there are few of them properties which are different from each other, that is from lanthanoid and actinoid. They shows different properties also, as well as they shows few properties which is similar in both. Then first we will discussing the similarities in actinoids and lanthanoids. Actinoids and lanthanoids. See here, first focus on it that both are inner transition elements. That means here in both n-2f orbitals are progressively filled up. That means in lanthanoid 4f orbitals are progressively filled up, and in actinoid 5f orbitals are gradually or progressively or successively filled up. Then second one, that is both, that means actinoid as well as lanthanoids both shows common oxidation state, that is +3. It is because of the energy levels of n-2f, n-1d and ns orbital in both are nearly the same energies. Therefore the electrons from ns orbital and n-1d orbitals are loosened by those elements, and as ns orbital of lanthanoid and actinoid possesses 2 electrons in it, and sometimes there is 1 electron is present in n-1d orbital. Therefore when they loses electrons from ns and n-1d orbital, they shows the common oxidation state, that is +3 by both lanthanoid as well as actinoid. Then one more similarity is there, that is lanthanoids and actinoids both shows lanthanoid contraction as well as actinoids also shows actinoid contraction. All of you studied detail about that. That means as atomic number increases in series from left to right, that is La to Lu in lanthanoid, and in actinoid from Ac to lawrencium, atomic radii or ionic radii decreases from left to right in series, that are called as lanthanoid contraction or actinoid one, and in both series this contraction is observed. Then see here, the one more similarity is there, the elements which is present in both series, these are metals. Generally these are inner transition metals. That means they have less electronegativity. That is they are highly electropositive in nature. Therefore, they are highly reactive in nature. Reactivity of those elements present in both series that are highly reactive in nature. Then see here one more property which is same in both actinoid as well as lanthanoid, that is the salts of those elements, that is actinoid as well as lanthanoids, that is present in nitrate form, perchlorate form, sulfate form, hydroxide form, fluoride form, carbonate form and oxide forms also. They out of these nitrate form, perchlorate form and sulfate form of salts of actinoid as well as lanthanoid, these are soluble in water. That means sulfate salts, perchlorate salts and nitrate salts of actinoids and lanthanoids are soluble in water, while hydroxides, carbonates, as well as their fluorides are insoluble in water. That are the similarities found in both lanthanoid as well as actinoid elements. Then there are some differences in the properties of lanthanoid and actinoids. Therefore, I am going to discussing with the differences in lanthanoids and actinoids. Then first one difference, that is both shows +3 common oxidation state, but besides that lanthanoids which shows +2, +3 and +4 oxidation state, but actinoid shows the higher oxidation state, that is +2 to +6, and sometimes it shows +7 and +8 oxidation state. That means see here lanthanoids shows only +2, +3 or +4 oxidation state. That means higher oxidation state in lanthanoid is +4, that is cerium shows +4 oxidation state, and in actinoid they shows +2, +3, +4, +5, +6 oxidation state. That means they shows higher oxidation state, and sometimes they shows +7 and +8 oxidation state also. As they shows higher oxidation state, that is exhibited by actinoids, they have high tendency to form the complex, high tendency of formation of complex, and lanthanoid have less tendency of formation of complex. Then all of you studied about that the complex formation is always takes place in higher oxidation state. Therefore, actinoid have high tendency of formation of complex, while lanthanoid has less tendency of complex formation. Then see here one more property, that is in lanthanoid series only PM is radioactive. While in actinoid all elements, that is all actinoids are radioactive in nature. Radioactivity, that is radioactive elements. Then most of the lanthanoids are colorless. And they are fairly colored, while actinoids, few of them are colorless or silvery white, but most of them are colored elements. Colored elements. The one more difference which is shown by actinoid and lanthanoid, that is actinoids have tendency to form the oxocations. Actinoids have tendency to form the oxocations. Oxocations. What are oxocations? Oxocations means oxocations. That means those are the elements which having tendency to form the cations in their oxide form. That means elements have tendency to form the cations, but here actinoids have tendency to form the cations in their oxide form. That means it forms uranium oxide cation as well as it forms oxide of plutonium, and it forms the oxide of oxocation of Neptune, like this. See here, these are the examples of oxocations shown by the actinoids, but these type of oxocations cannot be formed by lanthanoids. These are the differences in the lanthanoid and actinoids. Then all of you studied about that lanthanoids and actinoids, that is inner transition elements. These are placed or lies between NS orbital elements, that means S block elements, that is pre-transition metals, and transition metals. That means lanthanoids lies between pre-transition metals as well as transition metals. Sometimes lanthanoid shows the properties of pre-transition metals and transition metals. Then we are going to discussing on it, that is the properties or comparison between pre-transition metals, lanthanoids, properties of lanthanoids, and transition metals. Transition metals, these are mostly D block elements. Pre-transition metals which are present in S block elements, and lanthanoids which are inner transition elements. See here, generally pre-transition metals in which NS orbitals are filled up and they shows monovalency. That means these elements are monovalent. While lanthanoids shows +2, +3 and +4 oxidation state. And all of you aware of that transition metal shows variable oxidation state. Variable oxidation state. Here that oxidation state they shown exhibited by those elements, that is +2 to +7 and +8. That is they shows variable oxidation state. Then see here that contraction in those series is very less or negligible. That means contraction takes place in the period and it takes place at the last, at the noble gases. But here contraction is negligible, or it is observed at last, that is at noble gases. But in lanthanoid contraction takes place. Lanthanoid contraction takes place. In transition element, contraction is there in series, first series, second series, third series and fourth series in transition element. But that contraction takes place in series, in transition series, is less than the lanthanoid contraction. Then see here, these are highly electropositive in nature, therefore they have high metallic character of pre-transition metals, therefore they are generally hard, and they are oxygen, halogen and nitrogen donor. That means they forms the compounds with oxygen, halogen and nitrogen. Similarly, lanthanoids are also hard and they also forms the compounds with oxygen, halogen and nitrogen. And see here, transition elements, most of them are soft because of their variable oxidation state and some few properties which makes them soft. Then see here, in pre-transition metals, that is first group and second group elements, in group the element shows similar properties. They show similar properties in elements in the same group. Here lanthanoid also shows the similar properties. Same properties are observed in elements of same series, that is lanthanoid series, but there is variation in the properties. Variation in the properties of first transition series, second transition series, third transition series and fourth transition series elements. There are few variations in the properties of first, second, third and fourth transition series. Similarly, see here, in pre-transition series, they shows poor coordination number. Poor coordination number, that means they does not have tendency to form the complex. There and here lanthanoid, which shows the coordination number, that is higher coordination number. They shows 8, 9, 10 and sometimes this shows 12, that is higher coordination number. Therefore lanthanoid has tendency to form the complexes than transition metals and it is more than pre-transition metals. Transition elements which shows typical coordination number, that is 6. Most of them shows the 6 coordination number and they forms the complexes in coordination number 6. Then see here, pre-transition metals which does not shows magnetism, that means magnetic behavior, that means does not shown by the pre-transition metals, but magnetism is shown by the lanthanoids. Most of them are paramagnetic and few of them are ferromagnetic in nature, while transition metals also shows magnetic behavior or magnetic property which is measured in the form of effective magnetic momentum, which is measured in Bohr-Manton. Then these are the few differences or comparison in the properties of pre-transition metals, lanthanoids and transition metals. Now I am going to discussing with you the last point of this chapter, that is applications of actinoids. All of you studied the elements present in the actinoid series, that are radioactive elements. Out of that, uranium and thorium, which is present in the nature, or it is found in the nature, which having the half-life period is very long. Therefore their radiations are very little or less. Therefore these elements in their different oxidation form, they are used in everyday life. For example, see here, thorium in +4 oxidation state, that means here thorium oxide and 1% cerium oxide. The mixture of these two are used in indoor lightning. Because see here, why these are used in indoor lightning? Because mixture of these two, that is thorium oxide and 1% cerium oxide, oxidizes the natural gas. Natural gas, when oxidizes, and the heat liberated during this process is converted it into light energy. That means those oxides converts heat energy of burning of natural gas into light energy. Therefore, these are used in indoor lighting. Nowadays, demand of these increases and therefore these are also used in outdoor lighting. Then uranium. All of you studied about that. Uranium, which is used in the nuclear reactor. It is used in nuclear reactors to produce the lot of heat energy to convert it into electrical energy. That means uranium is used as a fuel which is used in nuclear reactor to produce the heat energy, and that heat energy is converted it into electricity. That is about the applications of actinoids. Then we will see one more point, that is the last point, post-actinoid elements. All of you studied the actinoid series elements, in which uranium which having atomic number 92 and the elements after uranium, are called as, that means the elements which having atomic number 93 to 103. These elements are known as transuranic elements. That means here the elements after uranium are called as transuranic elements. Most of them are synthetic in nature. That means they are prepared in the laboratory artificially. Therefore, these are used in different nuclear reactions, or these are prepared by different nuclear reactions, of which the short life period is very less. Then see here the elements which having atomic number 104 to the element which having atomic number 118. These elements are known as post-actinoid elements. That means the elements after actinoid series which having atomic number 104 to 118 are called as post-actinoid elements. And see here, out of this, the element which having 112 atomic number, which having the half-life period, that is 2.8 into 10 raised to about -4 seconds. That means they have half-life period in milliseconds and they are highly unstable elements. See here, the Rutherfordium, the element which is present in post-actinoid elements, which forms the ReFCl4 like halide compounds in +4 oxidation state, similar like zirconium and hafnium. That means they shows the properties like D block elements, that is transition elements. Similarly, dubnium which is post-actinoid elements, which also shows the properties like transition elements of niobium in its +5 oxidation state, which is transition elements, and it is also shows the properties like proctatinium. That is, it also shows the properties like proctatinium in +5 oxidation state like actinoids. That means these elements shows the properties like actinoids as well as transition elements. And that is about the actinoid elements. Now we will stop here. The topic is completed, and do the exercise. Thank you.
Solve test given to you in your notebook. Thank you. Thank you all.